All right, so we're going to start looking at kind of the most basic setup of a circuit with both a resistor and a capacitor and look at what happens in that circuit. These circuits are generally called RC circuits. The term RC comes from a resistor and a capacitor within a circuit. And these circuits actually show up in all sorts of different places when we start to look at them in electronics. I'm willing to bet if you open up really any electronic device you have sitting with you, you're going to find an RC circuit somewhere. One of the best examples of a device that has a very simple RC circuit in it is something like a disposable camera. If you look inside a disposable camera, there's a battery pack, there's a resistor, and a capacitor. And when you turn on the charge of a disposable camera, that capacitor charges up. You'll actually hear kind of a humming, whistling sound as that capacitor charges up. I'm not really sure where that sound comes from. And what starts to happen is you start to add charge to that capacitor in the flash. And when you push the button to take the picture, what happens is a switch flips and all of that charge and current is released through the flash bulb, and it causes a quick, bright flash. And so that's one example of where we'd use this type of circuit, is if we want to store charges for a short period of time and then discharge them somewhere else. Something like a disposable camera would be a good example. Another type of device that law enforcement uses, a non-lethal weapon called a taser or a stun gun, essentially has an RC circuit that does something very similar. You charge the thing up, it stores the charge in a capacitor, you push the button, it releases that charge over a very short period of time, and you discharge the capacitor. These can also be used in timing devices, and we'll talk about why that is in a little bit, because certain elements of this circuit provide a very resilient and very consistent way to measure time. So let's look at charging an RC circuit. So let's say we have a circuit that contains a battery, a capacitor, and a resistor. And so maybe this circuit here, and we've just flipped the switch up to point A. So we have something that looks like this, really. What happens is we have a current I that's going through the circuit. Really, all the voltage drop in this circuit is on the resistor because initially there's no charge stored on the capacitor. Since the voltage drop across the capacitor is C related to C and Q, well, if there's no Q, there's no V on that capacitor. So as Q increases on the capacitor, the voltage or potential drop on the capacitor increases, the voltage drop on the resistor decreases, and what also happens is the current decreases as a result. And so we ultimately end up with a state where the charge of the capacitor is up to the maximum amount of charge, C times V. So all of the potential drop is on the capacitor. There's none on the resistor. That means we can't store any more charge on the capacitor in this setup, so current is zero. So we start with this initial case, and we end up with this final case. I would actually call this the equilibrium condition or the steady state condition for this capacitor. We can actually measure a formula for how the charge on the capacitor increases related to other things in this circuit. And that formula looks like this, that the charge on your capacitor is equal to C times V, where V is the voltage of your battery and C is the capacitance of your capacitor. That happens to be the maximum charge that you can increase, times this formula 1 minus E to the negative T over RC power. If we looked at current, what current would look like is V over R. Well, V over R is the initial current. The moment you start charging this capacitor, it happens to be the maximum current, times E to the negative T over RC power. Now you can get this formula by applying the fact that the derivative of charge with respect to time is equal to current. Now this value RC actually has a term name for it. It's what's called the time constant. And what the time constant really does is it's a way to measure the time that it takes for the charge of the capacitor to become 63% charged. So if you started at 0 charge, how long does it take to get to 63% of that charge? Well, happens to be the time constant, R times C. if you actually work the units out in R and C, you find that you do get a unit of time for RC. So where this 63% really comes from is really it's out of the mathematics of how this thing actually becomes charged up as you work out. Now it's worth pointing out that this is a constant 63%, so for each time constant, your charge earns 63% of the remaining charge left over. This is an exponential function. If you actually were to graph this function, you get something that looks something like this here when you graph this function. We'll play around with that a little bit in class too as well. It's worth pointing out that if you are in biology with Miss Inman at some point, or Miss Deneen, or one of the other biology teachers, you've probably seen a function that kind of looks like this, because this also is a way you can model population growth. So let's look at discharging a capacitor. So we've taken and we've removed the battery, we've flipped it around so that now just the capacitor and the resistor in a circuit. Now the capacitor kind of acts like a battery in this circuit. So we have Q equals CV, current flows through the battery, and we can actually measure that current equals IR. So current flows from the positive end to the negative end of the capacitor. As current flows, well, we use up Q. That means that the voltage or potential across both capacitors gets smaller, both the capacitor and the resistor gets smaller and smaller. And it also means the current gets smaller as this process goes on. Where this process ends is there's no charge left on the capacitor, no charge is left to flow, so there's no current, and so there's no potential drop across the battery. We've used up all the charge that was stored in the capacitor. Now, if we want to actually work out what this function looks like, we get Q equals Q initial, whatever the initial charge on the capacitor is, times E negative T over RC. And the current, if we take the derivative of this thing, we get negative Q over RC, which is the initial current of this system. Remember, Q over C is the initial voltage, V divided by R is current, E to the negative T over RC. And again, RC is the time constant, and what the time constant really relates to is how long does it take for 63% of the charge on the capacitor to become discharged. It's worth pointing out that this function here also probably looks familiar to you. This is basically your exponential decay function. So let's do a quick problem, and what I have is a situation where I have two resistors connected to this circuit with a capacitor in it, and I've connected them to a 10-volt battery. And so we're going to flip the switch to charge the capacitor, and then we're going to eventually open up the switch to discharge the capacitor. So switch S is closed, and what we want to do is figure out at the moment that switch S is closed, what are the currents through the two resistors, and then what happens when the capacitor is fully charged. What happens to the current through these two resistors? So if we flip the switch, what's true is that the capacitor has no potential drop across it. There's no charge stored in it, and so we can actually ignore it in the circuit in the initial state. It effectively is doing nothing at this point at the moment the switch gets flipped, because there's no charge stored on it. So this really looks like the moment the switch is flipped, a simple parallel circuit with 200 kilo ohm resistors in it. So what's true is the voltage across each one should be the same. We could do I equals V over R. V is 10 volts. R is 100,000 ohms. So you get a current of 0.1 milliamps across both of these resistors the moment the switch is closed. Now what happens as this charge builds up on the capacitor? Well, what happens is the voltage on the capacitor increases. The voltage on this resistor decreases, and we ultimately end up with a situation where the current through R1 is 0. Well, the current through R2 hasn't changed any. It's still 0.1 milliamps because it's still connected in parallel to the battery. So the current on I1, or R2, stayed the same. The current on R1, when you flip this switch, well, it should really start at 0.1 milliamps and decrease to 0 as the capacitor gets charged. Now my next two questions, what is the total amount of charge that gets stored on the capacitor? And then what is the current in R1 and R2 the moment I open the switch once the capacitor is fully charged? Well, if the capacitor gets fully charged, it means that all the potential drop in this loop of the circuit is on the capacitor. So really, your potential across the capacitor is 10 volts. And so we can actually calculate out the total charge. 2.5 millicoulombs is the total charge. And what happens when I open the switch? Well, then you have a circuit where the capacitor is going to discharge. And you actually have what looks like a simple series circuit with 200 k ohm resistors in series with one another. And so the equivalent resistance is really 200 kilo ohms. We still have 10 volts as our total potential the moment the switch is opened because, well, all that's stored on the capacitor. And so our total current would be 0.05 of a milliamp through both of them. It's worth pointing out that this current is going to decrease as the capacitor discharges. The last question I have is, how long is it going to take for half the charge on the capacitor to be dissipated or to discharge? Well, we could use my charge formula. If I solve this for Q over Q0, what half the charge means is that I have half the charge remaining. So the ratio of Q over Q0 is 0.5. We know R and C. So I could actually calculate out T. The way to get rid of the exponent is take natural logarithm, multiply everything by negative RC, and you actually get that it takes a really long time, 3.47 times 10 to the 5th seconds for this circuit to be half discharged, or about 9.6 hours. So this combination of resistors and capacitors probably is not a good combination for us to do in a lab experiment just because it takes so long for it to actually discharge. This might be one where we would set it up and let it discharge overnight to figure out what actually is going to happen in that circuit. So looking in the next lesson, we'll take a look at this system in a little bit more detail and apply some calculus and come up with what the differential equation for both charging and discharging looks like, and talk about some ways that you could get the charging and discharging equation from that differential equation.